integrals using polar coordinates. Hopefully we'll get finished that today. Here is a question which is asking us to find the volume of this solid above this region. So if you can imagine what this region is, it's a complete circle, right? But that would be on the floor. But you can imagine above this circle, there's a curved surface. And so when they ask you to find the volume, they are essentially asking you to find a double integral, right? So if you think, what is a volume, or how do I calculate a volume? D is the XY plane, if you like, the floor of the shape, and then you go up to the curved surface, and the volume you're calculating is, what does that circle look like when it has a curved top to it, typically? In metal. So in polar form, I've chosen a really nice, easy one to get started. And would you agree it's a complete circle? Everybody is a number. Wouldn't that represent D? Agreed? No biggie here. And so I'm going to do from theta equals 0 to theta equals 2 pi. I'm going to do r equals 0, in this case, to r equals 7. That guy turns into r squared. Remember, there are certain combinations of x's and y's that turn into polar form really nicely, isn't x squared plus y squared r squared. And then instead of dA, don't we do an r dr d theta? Everything cool? Right. So the volume is equal to this double integral. This particular double integral is separable. And there are two features that a double integral needs in order to be separable. And the first one is both the limits of integration must be numbers, right? You're not allowed to have r equals 0 to r equals cosine theta. You cannot separate a double integral if that happens, all right? So they both have to be numbers. And the second one's a little bit more obvious. Doesn't the function have to be separable, right? So you can separate r cosine squared theta. You cannot separate r cos theta plus r cubed, right? Something that's not separable, right? Now, the only guy that's missing, and I'm pretty sure I mentioned it yesterday, but I'll ask you again. This one, r cubed, pretty obvious. What goes here?
1.
1. And if you integrate this, you're going to trust me, but you get 2 pi. And if you integrate this, you get 1/4 r to the 4 evaluated at 0 and evaluated at 7. And I'm going to find out what r to the power of 4 is. So that's 7 to the power of 4. It's a ridiculously big number. So it's 2 pi times 2401 quarters. And that cancels with that. And so you end up with, what do you end up with? 2401 over 2 pi. Unless the question specifies otherwise, we expect a whole number for, not a whole number, but an exact value for the answer. Are we good? Now, here is another double integral, which is actually quite easy to do because everything has been set up for you. Are you comfortable about that? Right, they give you, right? Now, if you want to take this function, it can be separated as well. Oh, no, it can't, that guy there. So you're going to do 0 to pi, r equals that to r equals that. So I should have put my r's in. for me. That's going to get you 5 halves r squared, evaluated at 0 and at 1 plus cosine theta. Now, the reason that couldn't be separated was because one of the limits of integration had cosine theta in it. And what I'm going to get is 5 halves, 1 plus cosine theta squared d theta. Right, now we're into Calc 2 world, where we're trying to integrate a function that has got a little bit of an awkward look to it. Any suggestions about what the next line of working might look like so that I can actually get an integral that I can do? Because right now I can't do it. And I don't know why I put r there, these are theirs. What could you do with that expression to help you get closer to finding the integral?
Multiply it out.
Okay. Can I pull out the 5 halves, because they're a pain in the butt when you get fractions, and just multiply out this? And if you do it, you get that. So that was a good start. Everybody comfortable with that? Now, I know how to integrate 1. I know how to integrate 2 cosine theta. I have to figure out what cos squared theta is going to be. And I know we did one of these yesterday. Does anybody remember another way to write cosine theta, which is going to help us?
Isn't that 1 minus, or 1/2 1 minus cosine 2 theta? I got the sign wrong.
Yeah, but you're close enough. Yeah. Now, this is pretty much at the end. A half and half gets you 3 halves. You have a 2 cosine, and you get a half cosine of 2 theta. Right, at that point there, I think I can leave it. Would you agree that integration is relatively straightforward now? And I believe they tell me that the answer ends up being that. I'll take their word for it. Now, question 8. Is it 18? I'm doing 18, but do I want to do anything before that? No, I want to do 18. Imagine that you're being asked, and I'll draw the picture they've got only because it kind of helps me. And you have a shape that looks like this. And this happens to be the curve r equals the square root of theta. And we are being asked to find the area of this shape. 3 exclamation marks. You told me that the double integral only finds volumes. And the answer is yes, it only finds volumes. Yet I can adjust it to find areas. And this is the cheat. If I take this shape and make it 1 high, which is basically what that is, right? Won't the volume of a shape that's 1 high be the same thing as the area of its base? Does that make sense? Area of base times height. If you make the height 1, right? Volume and area are the same number. That's kind of the argument. So we are going to find double integral of this guy and it's going to be equal to the area. And you get that by finding that guy. So the area of D will be this. So if you want to find the area of any shape, can't you just do a double integral with a 1? Kind of clever, right? Now, that's going to be 2 guys that I haven't done yet. 1 times R, dr, d theta. So far, so good. Now, this shape, right, this region D that we're trying to do a picture of, has an R constraint and it has a theta constraint. The R constraint is here. You see how that gets incorporated? Right, if R is the square root of theta, and you do any random projection line, won't it start off at 0 and finish off at R equals the square root of theta? Do you see where that comes from? Now, the next one's not so obvious, but I'm just going to tell you and hopefully you agree. That shape starts off with an angle of 0. I know it's hard to tell, but can you imagine it curves right round like that? Starts at 0 and you finish at 2 pi. So we will now have theta equals 0, theta equals 2 pi, R equals 0, R equals the square root of theta. And now you are done. So double integrals are useful for finding volumes. And if you do this little adaptation, can you also use it to find the area of the D, the base shape? By just making your height 1, essentially. And anything else here? Done that, that's good. Question 19 is watch a video and do it. Question 20 is watch a video and do it. So we are done. Is there any questions about double integrals and using polar that you want me to talk about before we move on? Last chance? Okay. Oh, yeah, keep it. Never know. So we are moving on, and we are now going to do Math 264. Get the title up here. And the section is 15.4, and it's called Applications. This is one of those sections where I feel uncomfortable because I'm not an engineer. And so I apologize beforehand if I describe things in a way that somebody who is an engineer would say, well, that's not really the way we say it. Right, but whatever. Here we are going. Actually, let me show you the questions, at least one of the questions, just as a starter. Can I make this guy bigger? Cool, right. So here is an example of double integrals being used in a real, no, it doesn't look right. Right, can you see question 1, electric charge? Right, now if you're not going to be an engineer either, don't get too caught up on the details. Think of what's going on as there's going to be a double integral involved, and it's going to get me the answer to something that an engineer or an electrician would like to know. So in this story, the electric charge is distributed over a rectangle. So the rectangle goes with an X value from 0 to 8 and a Y value from 5 to 8. And it's done so that the charge density at XY is given by this. So they have a function called the charge density function, and it's 4x plus 6y. And they go and they tell me it's coulombs per square meter. And then they finish with find the total charge. Now, if you were an electrician or somebody in electrical engineering, you might say, ah, that's interesting. That's something I might want to know one day. How could I, how would I be able to do that? And if you're not, you have to think of this as, how can I get a double integral to do what they want me to do? So here goes. Isn't this D? That makes sense? Right? And I know we've just finished doing polar, but that doesn't mean everything from now on is polar. Isn't this much more double integrals like beginning of last week, right? So double integral. Now, isn't that guy really my f of xy? Now, in this case, it's a charge function. Couldn't the next time it be a density function, which basically tells you how heavy the plate is at given points? Couldn't it the next time be a temperature function, right? It tells you the temperature on the plate at a given time, right? It's just a function that says at every value of x and y, something is happening there that we are measuring. We're measuring charge, heat, magnetism, weight, I don't know what else, light. You know, how much light is in that one spot. So when they ask you for the total charge, you're going to say a double integral of my function, dA. And then you're going to say, in this case, it's going to be from x equals 0 to x equals 8, from y equals 5 to y equals 8. And the function that you're, in this case, it's a charge function, dy dx. Are you comfortable about how I created the double integral for that question? Even if you don't know what a coulomb is, in a way, it didn't really matter, right? As long as you didn't get too caught up on the weeds. You've got a region, you've got a function, you want a double integral because double integrals add up everything that's happening. In this case, it's adding up all the charges. Maybe the next time it's going to add up all the temperatures or all the magnetism or all the heat or whatever else, all the light. And at this point, I'm going to dot that. Would you agree that's a pretty easy double integral to do? Right? Can't separate it, unfortunately, but the numbers are quite nice. And that was our first problem. Now, in question 2, we have a plate, and this plate has a density function, which is basically equal to that. And on this plate, it's positioned on the x and y axis, and there's the origin. So there's my D. And, well, I can't do it, but basically they say on this plate, it's light on this side and it's darker from the other. So you can imagine it's very pale and then getting really dark towards the end. And that represents the density. In other words, this is a plate that at this side here, the metal is very dense, right? It's heavy metal. And over here, it is quite light, right? So this plate has different densities, right? And this number is 1 and this number is 1. And we are being asked to find what's called the center of mass. And I will get to him. But before we do the center of mass, let's find a guy called the mass, or if you want its full title, the total mass. So aren't I basically just going to add up all the different densities here? So it's going to be a double integral of d of my density function, dA. And in this case, the x's go from 0 to 1, and the y's are going to go from 0 to 1. And the density function is whatever the value of x to the 4 is. and we're going to do a dy followed by a dx. Right, has anybody got an idea here about an easy way to calculate this function? I mean, I could just do it the way it's written, but is there an easier way to do that?
Separate it.
Why don't we do that then? X equals 0 to x equals 1 of x to the 4. And y equals 0 to y equals 1 of 1. Trust me, that ends up being 1. This ends up being 1/5. I mean, I'll let you do the calculations, but can you trust me that's what you get? So the answer that we get out of this guy here is 1/5. Are we good so far? No problems, right? Total mass, total charge, total temperature. The minute you see a word total connected to it, it's a double integral of some function, in this case, the density function. Now the new guy. Before I go and show you the formula, let me give you a little kind of rundown of what center of mass is. Going to take the simplest situation. Here we have a metal plate that is the same mass throughout, right? So it's not denser on one side than the other. The center of mass would be there. We call the center of mass x bar, y bar. So if this plate, let's put in my x and y axes. So if this plate went from 0 to 10 and 0 to 8, that guy there would be 5,4. And that's what we would call the center of mass. It's a coordinate that tells you where that shape would be balanced. So if I took that and I stuck a pen right under that dot, wouldn't that plate, theoretically at least, wouldn't it balance? It wouldn't be falling over, right? If I put my pen here, wouldn't it be lopsided and it would fall off? Knowing the center of mass of a plate or a two-dimensional surface is very important, because if you want to make something that's stable, don't you want to know where the center of mass is, right? It kind of makes sense, right? If you do ships, for instance, I know they're three-dimensional objects. If you want a ship to be stable in the sea, oh, wait a minute, we have people. Christian, I've changed my mind. It's a submarine, right? If you have a submarine, where do you want the center of mass to be to have a submarine that's stable in the water when you're traveling on surface or underground, undersea? Where do you want it to be?
Usually we keep it in the middle.
Right? And probably as low down as you can, so that when you're on the surface, there isn't a tendency to keel over left or right, okay?
Yeah.
Now, if you had a center of mass that was much further forward, wouldn't that submarine have a tendency to want to dive as you traveled horizontally? It would be nose deep, right? You don't want ships to have their center of mass here. Wouldn't that ship dig into the sea as it's traveling, right? So center of mass is a pretty big thing to be aware of. And I'm telling Christian, but he knows this anyway, because other submariners have told me this in the past. On submarines, they move the weight around, ballast and water. And the reason they keep doing that is to try and get the center of mass where it should be. Right, so if you fire a couple of heavy missiles, you better figure out a way of moving the weight towards the middle again, otherwise you'd be in trouble, right? So, have I convinced you? You need to know center of mass. Right, it's a good thing to know. Now the messy part. It's not as clean as you want it to be. First thing you're going to do is you're going to calculate two guys. One's called my and one's called m little x. And my, the first one, is the moments about y. That's their name. And mx is the moments about x. And I'm only telling you that because they told me. It's not a thing I'm interested in, but that's the name of them. And if you want to calculate m of y, right, it's the double integral of x, your density function, dx. And if you want to calculate the moments about x, it's the double integral of y, the density function, dA. Now, the first thing that annoys me is the naming kind of looks back to front. Do you notice that my has an x here and mx has a y here? Wouldn't it kind of make sense if x has got your x's and y's got your y? So be careful of that, because the most common mistake that I make is I forget that and I switch places. So if my center of mass is 5,3, I end up writing 3,5, right? Because I got them back to front. So be aware of that, right? The moments about y is x density. The moments about x is y density. Now, to get x bar, right, it's my, right, over the mass. And to get y bar, it's mx over m. And let me make sure that I got that the right way around. And I did. And again, would you agree that that notation is kind of back to front? Now, if I was starting naming things, do you know I would call that mx and call that my, because the formula would work really well with those names. But evidently there's some other reason why you don't do it that way, and I'm not going into it because I don't know, but evidently you have to look at things as rotating about an x-axis or rotating about a y-axis, and that's where these moments are coming from. So we got this package. We are going to put this package together to get the center of mass. So I want to just double check on my guy x to the 4. What's this one anyway? Okay, we disagree here. Oh no, God. For a minute, I thought I'd screwed this up, but it is 1/5. We are good to go. Okay, let's get my. It's going to be the double integral of x times the density function. And we're going to do x equals, let's get these now. Oh, they're both 0 to 1, right? So x equals 0 to 1, y equals 0 to 1. I'm going to do the x's and then I'm going to do the y's. But these guys separate anyway, so it really didn't matter. And you're going to trust me that that's 1 and that's a 1/6. So this guy ends up being a 1/6. Are you comfortable with the answer? Right. So we're now going to get the moments about x's, which is the double integral of y density function, dx, dy. And this does separate. That's where the y's go. And then it separates. This is where the x's go. And this guy ends up being a 1/2. And this guy ends up being 1/5. And so this guy is 1/10. And you can do the details later. But they're such long questions, I have to cut corners, right? Can you trust me that that's a 1/6? And can you trust me that that's a 1/10? So we are almost done. The x coordinate of the center of mass is my. Oops, which is 1/6, divided by the mass, which is 1/5, and that basically becomes 5/6. And y bar ends up being 1/10 divided by 1/5, and I believe that ends up being 1/2. And so our center of mass is at location 5, 6, 1/2. So if I imagine that is 0.5, right, and that's 0.5, the center of mass is 5, 6, 1/2. It's a little bit to the right-hand side. You see, that's not quite in the center. And the reason for that is, isn't this material much denser on this side, right? It's heavier here, and then it gets kind of lighter. And you see that that makes the center of mass like a magnet. Doesn't heavy bits drag the center of mass closer to it, right? And so that does make sense to me, that the center of mass would be a little bit off. Now, if the density function was just 5, right? In other words, everything weighed the same, wouldn't the center of mass be at 0.5, 0.5? Right at the center. Now, since these questions are really long, right? Right, there's a lot going on. You might want to do some shortcuts to try and cut down on your workload. One of the shortcuts I've been using a lot is variable separable, but there's another one. If the function is symmetric, can't you get the answer to each? In other words, the x bar and the y bar should be the same, right? So if your region is symmetric and the density function is symmetric, just find x bar. Y bar is going to be the same number. That can reduce your workload by 50%, almost 50%. This question, it didn't work. But can we pretend for a minute that the density function was that? Would you agree that's symmetric? And would you agree that this region is symmetric? Then wouldn't the x bar and the y bar be the same? In which case, I would be going, what was that, 0.6, 0.6, right? Because one of them was 0.6, so will the other be, right? Because I'm looking at a shape that's light and getting denser this way, and light and getting denser that way. So isn't there a kind of tendency to move you this way? So if the function, the density function is symmetric, and if the region is symmetric, right, it's balanced, only find x bar and y bar will be the same. I could have got that back to front. It could be that both of them are 0.5, but whatever it is, they're both the same.
Can I see the last page you had there?
There.
Thank you.
Can you tell I'm uncomfortable doing these things? I have no problems with math in general, but I do have problems trying to describe something that is not in my wheelhouse. But,
sorry, I meant the page after that one.
Oh, I didn't know we had one after that one. Here it goes. Well, that was the final answer. So the page that I had after that would be back to here, where I talked about if the function was symmetric, that you only need to find x bar, y bar will be the same number. That's pretty much all I was saying there.
Okay,
So
thank you.
Right, let's pick another guy. Yeah, trying to look at my time here. Oh, if it takes a while, it takes a while. In this particular one, our region D is a nice rectangle. It's x equals 1 to 3 and y equals 1 to 4. Nothing wrong with that. Our density function is ky squared. So there is no symmetry to anything, which means we have to do it the long way. So first you get mass. It's going to be the double integral of your density function, dx, dy, and the x's are going from 1 to 3, and the y's are going to go from 1 to 4. This is separable. So y equals 1 to y equals 4. I'll give that guy the k. And, well, there isn't really anything in the x's to worry about. So we get 1. That guy ends up being 2. And you just trust me on that. This guy is a pain in the butt, which means I'm going to have to do it. It's going to be multiplied by the power and reduced the power by 1. So it's 1/3 ky cubed, evaluated at 1 and evaluated at 4. So it's going to be 1/3 k times 4 cubed, take away 1/3 k times 1 cubed, and everything gets multiplied by 2. 4, 16, 64 thirds k, take away 1/3 k, everything gets multiplied by 2. 63 thirds is another way of saying 21k times 2. So the answer is 42k. And guess what? I did it right, so I'm pleased. So don't be surprised that you're going to spend a long time on these questions. So do it early rather than wait till Sunday, just so that you can get a half hour here and an hour there, you know, batter through 1 or 2 questions each time. Now, I'm going to do the moment of y's, which is the integral from y equals 1 to y equals 4, x equals 1 to x equals 3, and the density function is ky squared. Since this is my, do I put x here or do I put y here?
X.
Yeah. Remember that back to front thing? You put x. Now these separate, which is at least something. And if I can get any benefit at all, I'll do it. Would you agree I've already calculated that once? So I'm just going to say it's still going to be 21k. Comfortable with that? I've already found the integral of ky squared once. It was 21k. So if I have to find it again, can't I just use the answer? Now, what about this guy? Well, this guy's going to be a half x squared, which is a half 9, take away a half. So it's going to be 9 halves, take away 1 half. It's going to be 8 halves. It's going to be 4. So that ends up being 84k. And do a check on that? Oh, they don't tell me. Okay, I'll assume it's right. The moment about x's is coming up. In this case, that becomes y times ky squared. And that separates out as y equals 1 to 4 of ky cubed and x equals 1 to 3 of just 1. That one I don't want to do in my head, so it's 1/4 ky to the 4, evaluated at 1 and at 4. And this guy is just 2. If you plug in 4 here, you'll get 64k. If you plug in 1 here, you get, oh, come on, don't do that to me. You get negative 1k times 2. Yeah. 64, take away 1/4, turned into a fraction, is 255 quarters. Okay, times 2, which ends up being 225 over 2k. Okay, well, I should be able to do the centre of mass then. X bar is the moment around y divided by m. So X bar is that fella, 84k, and the mass is 42k, and that ends up being 2, which is correct. So at least I know I've done that one right. And Y bar is the moment around X divided by the mass. And that's the one that I'm not so comfortable about, but anyway, 225 2k divided by 42k. The k's cancel out. Let's see what that gets us. 225 halves, which is that, divided by 42, which is that. Math, turn that into a fraction, and I get 75/28. And darn it, I was close. The correct answer is 85/28. Can anybody see where I screwed up? That looks good. That looks good.
So I used the same input and got the right answer.
Oh, so you got 85?
I got 85/28.
Do you know where I hit the wrong button, or what? How come I didn't get 85?
I don't know.
No.
Isn't
Can you
it,
trust me? Yeah, say again.
isn't it supposed to be 255k divided by 2?
Oh, there you go. So I'm about to do that same calculation, and it better say 85, because I do not want to spend any more time trying to figure out what I did wrong. That guy divided by 42 turned into a fraction. Am I good or am I good? Yes, that's the right answer. Most of you know me by now. Would you agree this kind of question is fraught with danger with me? Digits disappear. I forget a number somewhere, right? It's got to be on your A game to get to that final answer. You could quite easily do 99% of this question correct and still get the wrong answer, couldn't you? I mean, the only thing that went wrong there was a simple transfer. Right? I just didn't write it down. Don't get too frustrated when that happens. Just think, I know I'm doing the method right. If I'm just a little bit more careful about the details, it'll come out. As long as you're doing the method right, that is fine. But unfortunately, we have reached the end. Maggie, have you got a joke to finish with while everybody puts their last name down? You got nothing for me? Christian, have you got a joke about submariners? No. Well, here's one for you. How do you sink? Right, you ready for this one? How do you sink a Polish submarine? You knock on the hatch. Was that bad?
That'll do it. That'll sink them. Yeah.
That'll sink it. Okay. Right. Bye-bye, everyone. Might as well leave you with a really corny joke. I'll hang about for any questions. Otherwise, see you tomorrow, where we get to do a whole batch more of these bloody things. Not my favorite, you can tell. Okay, Uni, question, Dylan, David, or Maggie?
Yep.
Right, what you got for me, Dylan?
So another one from the test from Saturday.
Okay,
Number 11.
number 11. Give me a minute to load that up. Here we go.
Do you mind if I stay, Dylan?
Ah, no problem.
Okay, so here goes. Number 11. Gotcha. And 11. Right, there are lots of places in this question that you could go wrong. So it could be quite easily a very simple mistake. But because WebAssign only wants the answer, you get the thing wrong if it's not the right one. So that will sort itself out in the midterm because I see all your working. So we have a triangle here and we have this guy. And the triangle has coordinates 1, 1, which is here. And then it goes 2, 3, 4, 1, which is here. And then it goes 1, 2, which is here. So this is my region D. And they want us to find the volume under the given surface. So the volume.
Mr. Robertson, we
You
can't
can't see
see
it?
the whiteboard.
Okay. Thank you. So in the question that we were talking about, this is a function and this is the region D that they're talking about. And they'd like to know what the volume of this surface would be. Can you imagine it floating up here? So double integrals over the region D of this function, which is basically the guy that goes there. That will get me the volume. So I'm going to have to set up limits of integration. It's going to be 9xy, and then it's going to be dx dy or dy dx. I'm looking at this question and both directions work, but when both directions work, I kind of go vertical, type 1.
That's the one I chose too.
So x is going to be from 1 to 4. And y, well, bottom value is 1, and the top value is whatever that straight line's equation is in terms of x. So I'm going to have to do a little side issue now, and that is find the equation of that sloping line. And what do I know? I know the top point has coordinates. What's that? 1, 2. Yeah, 1, 2. And this coordinate here has coordinates 4, 1. Right? And if you imagine that's my little triangle, and I do this and I do this, I can tell you that the rise is 1 and the run is 3. So I know that the slope is negative 1/3, right? Rise over run, pointing downwards. And now I'm going to use the point slope equation to get the equation of the line. And this is y take away, I'll use that one. Take away 2 is negative 1/3 x take away 1. So it's negative 1/3 x plus 1/3, and negative 1/3 x add 2 gets you 7/3. Did you get a guy that looks something like that?
Somewhat, yeah.
Yeah. See, if that's not exactly right, then your answer is going to be wrong, even although you've done most of it correct.
Yeah.
Just that's all it takes. So it's going to be, and I'm assuming I did this right. Possible I screwed up as well. Let's check. 1 to 4. That is 3. 1 down. Yeah, that's 1/3. 2. Yeah, that's 2. 1. That's 1. That's negative. That's an add. 2. No, I'm pretty comfortable now that that's right. In this case, the y's go inside. So there'd be y equals 1 to y equals negative 1/3 x. Add 7/3. And that means I'm going to do the y's before I do the x's. So, can't separate them because of this. So I'll do that guy first. With respect to y, you add 1 to the power and divide by the new power, which is that guy. And you've evaluated at 1 and at negative 1/3 x plus 7/3. So you've got an integral that looks something like this. When you replace y by this, you get 9/2 x, negative 1/3 x, plus 7/3 all squared. Take away, you plug in 1, and when you plug in 1, you just get that guy. So far, so good?
Yep.
Right. Nothing pretty about what's going to happen in the next few lines. Essentially, I need to integrate this, but I'm not be able to do it until this mess becomes a polynomial, essentially, right? So the integral from 1 to 4, I'm going to begin by squaring this guy. So that's going to get me 1/9 x squared. When you multiply this guy by this guy, you get negative 7/9, but you double it. So you will eventually get negative 4/9 x. And 7/3 times itself is 49/9. Take away 9/2 x. Now I'm going to distribute 9/2. 9/2 times this guy gets you 1/2 x squared. 9/2 times this guy gets you negative 7x. 9/2, no, x squared, x cubed, almost missed that. 9/2 x times this guy, the 9's cancel, you get 49/2. 49/2x. Take away 9/2 x. So you have 1/2 x cubed minus 7x squared. Those two guys, 49/2 take away 9/2 get you 40/2, which is actually 20x. So it's not as ugly as I thought it was going to be, but it took a while to get there. Now, add 1 to the power and divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Evaluated at 1 and at 4. So that's 1/8 times 4 to the 4. Take away 7/3, 4 cubed, plus 10 lots of 4 squared. Take away essentially 1/8 minus a 7/3 plus 10. God, this is not going to be pretty, but here goes. 4 to the power of 4 divided by 8. Oh, that one's pretty. It's 32. 7/3, which is that guy, times 4 cubed, which is that guy, turned into a fraction. Gets you negative 448/3. That guy gets you 160. Take away, I guess I should do this horrible mess. 1/8, take away 7/3, add 10, turned into a fraction. And that gets me 187/24. Okay, so I'm going to do that, take away that, add that, take away that, and hopefully calculator can handle it. 32, take away 448/3, add 160, take away that guy, take away 187/24. And then you do make me a fraction. And the answer I get is 279/8. Would you believe it? I got it right.